Hello, everyone, and welcome to the Stack Overflow podcast, a place to talk all things software and technology. I am your host, Ryan Donovan, and today we are talking about DNS and bind and the security implications of DNS. And my guest for that today is Cricket Liu, who's the chief evangelist at Infoblox. So welcome to the show, Cricket.
Yeah, thanks, Ryan. It's nice to be here.
So before we get into DNS and all that, can you tell us a little bit about how you got into software and technology?
Well, I majored in computer science in college way back when. I think my freshman and sophomore year, my computer science courses were taught on Vaxxon. That will serve, I think, to carbon date me, maybe.
Yeah.
I'd always sort of been involved in tech. The first job I took, actually, I worked there for 2 summers even before I graduated, was with Hewlett Packard. And back then, HP was a great place to kind of learn the ropes, learn how to do something useful, because I don't think I was useful to anybody right after I graduated. But I worked for the department that ran the HP Internet, then the world's largest private TCP/IP-based network, mostly because there were larger computer manufacturers, but they had proprietary networks, right? IBM had SNA, DEC had DECnet. HP really didn't have their own proprietary networking technology, so they mostly went with TCP/IP. And that was where I kind of learned the ropes. I ran HP.com for, about 4.5 or 5 years or so.
I think when most people think about DNS, they think about, resolving the URL of your website. But like you said, you got started on the internal network. There's a lot of DNS work that goes on there, routing internally. How does DNS work within a sort of, let's call it a captive network?
You have the same kind of infrastructure within a large enterprise network that you have out on the internet. You have recursive DNS servers, you have authoritative DNS servers. The authoritative DNS servers are there to advertise internal zone data. Most large enterprises have what we call split namespaces. So they have a different version of, say, infoblox.com that they show the inside, then they show the outside world. The outside world sees the website, the mail servers, the DNS servers, and things like that. Inside, you would see desktop machines, servers, information about applications that might be running and stuff like that. And of course, any large enterprise also has to have those recursive DNS servers, which are the ones that do all that heavy lifting of communicating with perhaps several authoritative DNS servers to find an answer. And some of those are looking up internal stuff, and maybe they just talk to internal authoritative DNS servers. Sometimes they're looking up stuff out on the internet, and they might have to communicate with external or internet-based authority. They might have to communicate with what we call a forwarder, which is kind of like a DNS proxy server, if you will, that assumes that responsibility on behalf of the internal DNS server.
So we've seen occasional cloud outages or infrastructure outages, and a lot of times DNS comes up as the culprit. Why is DNS sort of complicated, and why is it the thing that takes down, large parts of the internet architecture?
Well, DNS is simultaneously very, very fundamental in that it basically precedes every non-trivial transaction that occurs over the internet, but it's also not particularly well understood. And I've now spent almost 4 decades, I guess, doing DNS, and it's still not really broadly understood. You'd have a hard time finding somebody who's really an expert in DNS, which I guess means that my career has been something of a failure because, of course, I've been trying to educate people about DNS for those nearly 40 years.
Yeah. Well, you might be the expert they're looking for.
I was supposed to train other people. I guess it didn't go so well. But yeah, it's just not really well understood, despite the fact that that is this fundamental technology. I think people have, for example, a better handle on routing protocols like BGP and OSPF and other more exotic things. People understand email. There are certainly lots of folks who are experts in electronic mail. We probably used to have more DNS experts, but today, there are fewer and fewer of us dinosaurs out there, I guess.
I'm going to take the naive view here. Why isn't it just a list of IP addresses on the internet?
It was once. The ancestor of DNS was the host table, which is just a big file, and that file maps names of computers to their IP addresses. But in order to scale to a network as large as the internet is today, for example, in order to facilitate what we call delegation, so distributed management of this giant distributed database of named IP address mappings and named to other types of information mappings. We needed something considerably more complex. So that's why we have a hierarchical namespace we do in DNS, those dotted domain names that you see in all kinds of different contexts. All of that basically is necessitated by serving a network as large as the internet and providing that distributed management.
So when you have a number on a DNS or an IP address, is that always pointing to a single machine?
No, not always. So, for example, sometimes it can point to that IP address may be kind of a virtual IP address, and it might point to a load balancer, and or in fact, it may point to a whole system of load balancers, and those load balancers may decide on the back end which individual server they want to direct a request to. If someone sends a request to that single IP address, we also use techniques on the internet like Anycast. In fact, Anycast is used pretty widely in DNS infrastructure because sometimes you have a whole lot of DNS servers and you want to have them distributed around the globe, but you don't want to give each of them a unique IP address. You'd rather have folks refer to a single IP address and then just direct the requests to a DNS server that serves a particular function rather than a particular server.
Right. So then do those routers, Anycast front ends, do they have an internal DNS table or a DNS server that they look up?
Typically, when we're talking about what we call layer 3 load balancing, so that's load balancing that happens at the third layer of the OSI model, so basically where the internet protocol runs, they don't have to do any DNS lookups. They just say, okay, I'm going to map this virtual IP address to one of a bunch of other individual IP addresses that I know about. And then typically that load balancer has some mechanism for determining how it's going to distribute that load among those IP addresses. So it might do it in a very simple sort of round robin way. If there are 4 IP addresses, it gives the first request to IP address 1, the second one to IP address 2, and so on. Sometimes it tries to measure load on those backend servers and direct a request to the least heavily loaded of those servers. Sometimes it uses a different algorithm. And sometimes you, as the administrator of the load balancer, can choose which of those algorithms you'd like to employ.
As the local DNS expert, you wrote a book on DNS, but it's called DNS and Bind. What is Bind and how does it relate to DNS?
So Bind is an implementation of a DNS server. So DNS you can think of as a set of specifications, a very large set of specifications at this point. And DNS is largely documented in RFCs, which I'm sure your audience is pretty familiar with, requests for comment documents. Get any of these for free, download them off the internet and read about how DNS works. But you have to have implementations of those specifications. And Bind was a very early one of those implementations. I think Bind dates back to 1984. It stands for Berkeley Internet Name Domain. So that means it was written at my alma mater. For a long time, Bind was sort of the only game in town. It was by far the most popular DNS server out there on the internet. Nowadays, there are lots and lots of different DNS server implementations. Microsoft has one called the Windows DNS Server. There are excellent open source implementations like Bind. There's an organization in the Netherlands called NLNet that produces 2. One of them is called Unbound, which is a recursive DNS server, and one of them is called NSD, which is an authoritative DNS server. So yeah, there's a whole ecosystem now of DNS servers, but Bind is one of the grandfathers or grandmothers, if you will, of all of these implementations.
Yeah. Is it still in use much?
It is, as a matter of fact, despite the fact that it's been around that long, it's been extensively rewritten. The current version, the major version, is Bind 9. We started with Bind 4 back in the 1980s. Bind 8 came out, gosh, I want to say sometime in the 1990s, and I think Bind 9 after 2000. And we're well into the 9s. Right. This code probably shares no code with those previous versions of Bind. But yeah, it's absolutely still in use, and it's still one of the most popular implementations of a DNS server out there on the internet.
It's interesting that you say, like, it's gone through a lot of, might not share the same code. I can imagine part of that is the way, the internet has exploded and the infrastructure is, imaginary and managed for you. What are the major differences between a sort of 80s implementation of DNS and one today?
The folks at the Internet Systems Consortium, who actually are the caretakers of Bind, the folks who develop it, could probably tell you much more than I could. When it was rewritten for Bind 9, I remember that they were thinking a lot about multi-threading and multiprocessing because, of course, early implementations like Bind 4 weren't really written with multi-threading and multiprocessing in mind. They were also working to make the code a good deal more secure, to make it more auditable. And over the years, what we've seen is that the DNS standards have gotten more and more complex. For example, we fairly early on added things like dynamic update. In the 1990s, we started adding DNSSEC, the DNS security extensions. So there were architectural considerations when accommodating those new developments too.
I imagine it's the x86 specifications, another one that has extension on extension piled up over the 40, 50 years. Is the sort of weight of those extensions holding DNS back, or is DNS sort of adapting and remaining nimble?
I mean, part of DNS remaining nimble is accommodating those sorts of enhancements, those newer developments. So, for example, there were some new record types that were introduced partly to support Web3 because we wanted to give web browsers the ability to automatically discover which versions of HTTP were supported by a given web server, other sort of bootstrapping information before actually connecting to the web server. That just saves us time if you think about it, right? If we know, oh, that web server supports HTTP 3, I don't have to connect using just HTTP 1 or whatever and then fall back or whatever after I learned about its capabilities. So that's part, I think, of remaining nimble, part of adapting or changing with the times. But we are still, of course, asking a lot of the protocol. I mean, DNS for a 40-something-year-old protocol is still changing at a remarkably rapid rate.
Yeah. I imagine with the, just the speed that internet infrastructure changes. You said the DNS 9 was in the 2000s. Like, how many additional extensions have come in those 10, 15, 20 years, right?
It's, I think, a testament to the work that's done by ISC, the Internet Systems Consortium, and the community that develops Bind in particular, but DNS servers in general, that they've kept up with so many enhancements, so many extensions to the original DNS.
I think in the original email you reached out was you want to talk about DNS in a security context. So what are the security implications around DNS or security issues?
Well, we've had security issues with DNS for a very long time. Almost since the very beginning, we've had implementation flaws in different DNS servers, and folks have capitalized on those. There was an early worm on the internet called the lion worm that transmitted itself from computer to computer across the internet using buffer overrun in a DNS server as its main transmission vector. We have DNS servers that are the targets of big DDoS attacks. Back in, I think it was 2016, Dyn, spelled DYN, was the target of a huge DDoS attack, the largest, I think, that had been recorded up until that point. Took them off the air for hours and hours and hours in October of 2016. Made it look like the internet was down because they had such market presence. They hosted so many popular DNS domains.
That's the sort of fundamental piece of infrastructure that people don't think of. Like with the Dyn attacks, was it a single machine out there?
No, I mean, Dyn had a whole constellation of DNS servers, and they used Anycast, which we talked about a little bit, to sort of protect them, to distribute them around the globe. They had a pretty beefy infrastructure. But the botnet that was used to attack them, which was the Mirai botnet, was a huge, huge botnet comprising hundreds of thousands of CCTV cameras, DVRs that were used to store surveillance footage, most of them with high-speed connections to the internet. And you train that much bandwidth and anything, even a fairly robust constellation of DNS servers, you could probably take it down.
So you talked about Anycast. How does that work? Like, how does something do the routing to a multiple?
So if you imagine what we call an Anycast group, a bunch of DNS servers that all share the same virtual IP address, basically Each of them runs a routing process, not because you want to route through the DNS server, because you want to route to it. And the routing process basically advertises a route to the network that contains that virtual IP address. So you have all of these DNS servers in this Anycast group advertising that route. It all gets thrown into the great sort of routing mesh in the sky. And then when somebody sends a query to that virtual IP address, well, the routing mesh in the sky figures out, well, what's the closest instance of that IP address to me? That's where you end up having your request directed. Now, of course, it's also incumbent on the DNS server. If the DNS service stops responding for whatever reason, you have to stop advertising a route to that network. Because if you don't, then the closest folks to you are going to send you queries and you're not going to answer them because your DNS service is down. But it's generally speaking a very, very powerful mechanism. One, because it allows a tremendous amount of backend scalability. You can have hundreds of DNS servers all serving the same function on the back end, and they're all represented by just single IP address.
Yeah, I mean, I imagine that's how some of the larger cloud providers provide a sort of ephemeral routing to compute, right?
Yeah, that's right. So, I mean, if you think about, for example, public DNS services like Google Public DNS or Cloudflare's DNS, 8.8.8.8 is not one gigantic DNS server in the sky.
Right.
It's a whole cloud of Anycast DNS servers. Likewise, Cloudflare's 1.1.1.1 and 1.0.0.1 Anycast groups.
Mm-hmm. Something I heard from a recent cloud outage is that the DNS information was stored in a database that was then inaccessible when the DNS went down. Obviously, the DNS information has to be stored in a database somewhere. Is that an attack or issue that's happened before?
Well, I mean, that sounds like sort of a chicken and egg problem, right? Where if DNS goes down, you can no longer access the storage. So I'm not sure how you recover from something like that. Most DNS servers that I'm familiar with have some sort of local storage from which they pull their zone data, their configuration, and things like that. It would be a little fraught, I think, to try to load all of your data from some remote location. I mean, you could do that over time, but you would probably want to have kind of a bootstrapping process where initially you loaded at least the bare bones information you needed to access, for example, the remote storage that you needed to access and things like that.
Yeah. I want to ask about the IPv6 proposal. I know it's not DNS, but it's part of the infrastructure of it. It seems like it's something that's keeps trying to take off for, I don't know how long, a decade or so. Is that IPv6 solving a real problem, or is it sort of future looking?
Oh, IPv6 absolutely is solving a real problem, which is that we are effectively out of IPv4 addresses, other than folks finding IPv4 networks under their mattresses and dumping them into the big pool, or more likely selling them marketplace. We're basically out, and we still have tremendous growth on the internet that we need to accommodate. So IPv6 gives us basically limitless address space. It obviates the requirement to run nasty things like network address translation to work around this lack of IP addresses. And in some parts of the world and in some industries, IPv6 is super, super common. So, for example, any large mobile carrier uses IPv6 very extensively on their backbone networks. I mean, in the United States, we have backbone carriers, or we have mobile carriers who are large enough they can't use RFC 1918 internal IPv4 address space because they have more subscribers than there is address space reserved in RFC 1918, or I think there's some successor RFC.
It seems like one of those things that doesn't get visible to the public as much, right?
I think most people, for example, who use their mobile phones, they don't know what IP address that phone is using on AT&T or Verizon's network, and they don't really care as long as it works.
Right. And you said the nasty things like the network address translator. Why is that a nasty little piece of software?
Oh, network address translation causes all kinds of complexity and all kinds of problems. From a troubleshooting standpoint, it's difficult because if you're trying to figure out, okay, one of my employees isn't able to get to this website. Well, once you leave the boundary of your network, is his IP address translated to something else? If you're working with the folks who are actually providing the service, you have to figure out what that address was translated to. Generally, with network address translation, you have a whole bunch of source IP addresses that are translated to a single or a small group of internet-facing addresses, just using different ports. There are devices that have to do that translation that can break down or can run out of memory or any number of other things. We try to avoid it when we can.
It seems like my local router has its own network address, but at home I'm the 128 dot whatever. So we've talked about this sort of like scope of DNS and where it is. What are the current like difficulties with DNS as it stands now?
Well, I mean, one of the longstanding challenges with DNS was the susceptibility of what we in the business call stub resolvers, which is basically the DNS code, the client code that sits on every device that uses DNS. So on your laptop, on your phone, on your tablet, on any server, and it allows it to query a DNS server across the network, receive a response, and then interpret that response. That communication has traditionally been unencrypted. And that means that it's susceptible to both snooping. Some bad guy who has access to the network can actually see which websites you're accessing, where you're sending electronic mail, things like that, and also to spoofing. So a really bad guy could actually actively send back a response after reading your query and send you somewhere you didn't want to go, to some website that was masquerading as the one you thought you were going to, where you might enter your login credentials, have them stored and reused by the bad guys later on. So that's been a problem in DNS for quite a while. And within the standards community, they spent a fair amount of time on that and came up with a number of different flavors of what we collectively refer to as encrypted DNS. So it's encryption between the stub resolver or the DNS client and the recursive DNS server that it communicates with. By encrypting that channel, we can make sure that the data is private, that nobody can sniff it anymore and people can't spoof it. We can also optionally authenticate the server that you're communicating with. So this really is Infoblox on the far end of this communication, not somebody masquerading as Infoblox. You could even optionally authenticate the client to the server, but that would require more overhead.
So the encryption in transit, especially for web traffic, has been a sort of default for a number of years. Why is it taking so long for DNS traffic to be encrypted?
That's a good question. In fact, the protocols that we used in encrypted DNS were kind of borrowed from the world of the web. Mm-hmm. So there are sort of three big flavors of encrypted DNS. One of them is called DOT, which stands for DNS over TLS. One of them is DO, which is DNS over HTTPS. And the other is DOQ, which is DNS over QUIC. Mm-hmm. And you might recognize TLS as being the S in HTTPS.
Right.
And of course, DO is just DNS over HTTP over TLS. So all those technologies are borrowed from the world of the web. So I'm not sure I can give you any excuse why it took us so long to borrow those technologies from existing web infrastructure, but we finally got around to it.
Yeah. I mean, I could see an argument for compute on device or, package size or something, but it does seem like something it was like, come on, you guys.
It does place more of a burden on the DNS client or stub resolver and the recursive DNS server because they're dealing with encrypted communication. So when the stub resolver wants to send a query, it has to encrypt it. When the recursive DNS server receives the query, it has to unencrypt it or decrypt it. Likewise, when it sends a response back, it has to encrypt it. So all of that places more overhead on the DNS servers and clients.
Yeah. With DNS, places that they resolve to are sort of constantly being updated by providers around the world. Are there spoofing attacks, spoofing risks for those providers where you could update a DNS table with false IP addresses?
Yeah, I mean, we do see various varieties of attacks where, for example, there's one that my colleague Renee Burton referred to as a lame duck attack, where somebody notices what we call a lame delegation in DNS. So that's where somebody has at one point registered a domain name, foo.example, registered that, delegated it to a set of DNS servers, but then hasn't maintained it. And the delegation is now what we call lame. It
Right.
delegates to DNS servers that are either not responding or aren't responding authoritatively. Somebody comes in, some bad guy comes in and registers or corrects the lameness. So they come in, let's say the foo.example domain is delegated to some set of 4 name servers run by some DNS service provider. They create an account with that DNS service provider. And some of these DNS service providers don't do any sort of checking. They just go, oh, you're paying your bill? Great. You want to set up those DNS servers as authoritative for foo.example? Happy to let you do that. And so these guys have basically indirectly taken control of foo.example, and now they can basically act on the internet as though they were foo.example. And of course, in the real world, the folks whose domain names are being taken over have trade names, brand names that folks are familiar with. And there's the potential for a lot of reputational damage if somebody comes in and starts to abuse their reputation. The big thing that I think that I'm excited about anyway is that NIST just published a document called NIST Special Publication 800-81 R3, so revision 3. And this is the Secure DNS Deployment Guide. It's a document that's been published in one form or another since, I think, 2006. But in this latest version, they actually finally got around to covering encrypted DNS, which we talked about, but also protective DNS, which is DNS that's actually smart about what it will resolve. So DNS servers that know, hey, if you send a query to them for www.malware.org's IPv4 address, I probably shouldn't respond. I should probably say that doesn't exist. Tell you a little white lie to prevent you from going somewhere where your device might be infected. So that's a very exciting development for us, because I've been out snumping for protective DNS now since about 2010.
Yeah. So how do those protective DNSs get their smarts?
There are mechanisms that are built into a lot of DNS servers nowadays that allow them to apply reputational data. In Bind, for example, there's something called a response policy zone, or RPZ for short. But you have to get that from somewhere. You have to get that data from some organization. So there are providers around the internet who do really good work into, for example, analyzing spam and identifying phishing attacks and spam, extracting the domain names that folks are trying to lure you to, and then creating a response policy zone feed with that they can then provide to you. And my employer, Infoblox, does much the same thing in a slightly different way. We do it based on what we call passive DNS data. And my colleague Renee and her whole team of threat analysts do a fantastic job of running these machine learning algorithms that create response policy zones of literally hundreds of thousands or even millions of domain names that we know are being used maliciously out on the internet or are very, very suspicious, and you shouldn't go there.
Well, it is that time of the show where we shout out somebody who came onto Stack Overflow, dropped some knowledge, shared some curiosity, and got themselves a badge. Today we're shouting out a Populous badge winner. Somebody dropped an answer that was so good it outscored the accepted answer. So congrats to Johannes Schaub for answering, how do I check if a file is a regular file? If you're wondering about that, we'll have the answer for you in the show notes. I'm Ryan Donovan. I edit the blog, host the podcast here at Stack Overflow. If you have questions, concerns, topics to cover, if you want to yell at me, you can email me at podcast@stackoverflow.com. And if you want to find me on the internet, you can find me on LinkedIn.
And I'm Cricket Lou, Chief Evangelist at Infoblox. And you can find me at cricket@infoblox.com. And you can find Infoblox at www.infoblox.com.
All right. Thank you for listening, everyone. I will talk to you next time.